All right, in this unit, we're starting antiderivatives, which is exactly what it sounds like. It's the opposite of a derivative. So an antiderivative, a function f is an antiderivative of g of x if f prime of x equals g of x. So again, this is just the opposite of taking the derivative. So this first example, if f of x equals 3x squared, what is the antiderivative of that? So you might want to ask yourself, what, when I take the derivative of it, would give me 3x squared? And the answer to that, so we'll call this, we'll call the antiderivative g of x in this case. So g of x is x cubed. So that works. However, g of x could also be x cubed plus 1. It could be x cubed plus 2, and so on. Because when you take the derivative of this constant, that is 0. So all of these, if you took the derivative of it, you would get 3x squared. So the way we say that when we're taking an antiderivative is x cubed plus some unknown constant c. So that would be an antiderivative of 3x squared. So when you find an antiderivative, it's not the only antiderivative. There could be infinitely many. And this is the reason why, because you could put any constant there. So just another example along the same note, what's the antiderivative of f of x equals 4x cubed? So you just ask yourself what function, when I take the derivative of it, would give me 4x cubed, and the answer to that is just like last time. So this would be x to the 4th plus some constant c. So that's the general idea. And again, really important, you have to have that plus c. It's called the constant of integration. So the operation of finding an antiderivative is antidifferentiation, also called indefinite integration. They mean the same thing, neither one, so indefinite, neither one is better than the other. That should be an E. So indefinite integration. All right, so right here, we're just gonna make note of some symbols and terms that we'll be using. So this symbol that looks like an S will become your best friend. That is called an integral. So that tells us that we should be integrating. So, oops, integral. So that is called an integral. The function that you are integrating is called an integrand. The dx is called the variable of integration. So a variable of integration. And again, the plus c, we already said what that is. That's the constant of integration. All right, so now we have some basic integration rules. The first one, the antiderivative of 0 actually is c, so a constant c. Because if you think about that, if you take the derivative of a constant number, you would get 0. So this is the opposite of that. The antiderivative of 0 is c. The antiderivative of k, where k is a number, is that would be kx, because x is our variable of integration, plus c. Because if you think about this, if we took the derivative of k times x, it would just be k, and then the derivative of c is 0. So this is the opposite of that. We'll call this the scalar multiple rule. So if you have a number that's multiplied by some function, you can pull that number out of the integral if that's convenient to you. And again, this will be the sum. I guess we can call this the sum or difference rule. If it's convenient to you, you can split integrals up like this. So f prime of x and then plus or minus this one. So if that makes a problem easier, that's something you're allowed to do. Now, this is the big one for this section. This is the power rule for integration. So keep in mind that this is the power rule for integration. So it's the opposite of the power rule for differentiation. So if we're taking the antiderivative of x to the nth power, what we will do is add 1 to the exponent. Oops, a little ahead of myself there. What we'll do, so it'll be x and then n plus 1 in the exponent. So yeah, it doesn't look great either, so let's fix that as well. So x to the n plus 1, and then we will divide by n plus 1. So divide by that new exponent, plus c. So if you think about this, when we take a derivative, you subtract 1 from the exponent, and then, well, actually, I'm sorry, you bring your exponent down in front, and then you subtract 1 from the exponent. This is just the opposite of that. So let's look at some examples here. So this is the antiderivative of 3x dx. So this is 3 times x to the first power. So we are going to use the power rule here. And we do have a scalar multiple, so we can kind of pull it out just to make life a little easier since we're just learning this. So the 3 is just multiplied on the outside, and we're taking the antiderivative of x to the first power. So this will be 3 times, and then we add 1 to our exponent. So 1 plus 1 is 2, because this is x to the first power, so 1 plus 1 is 2. And then we divide by that new exponent. So this, well, let's just simplify it. So we have 3 over 2 x squared plus c. So that is our antiderivative. And again, I'm going to point out that if we took the derivative of this final answer, you would bring the 2 down in front. And the 2 would cancel out with this 2. And we would just be left with 3x. So this is our antiderivative here. So this one, I want to rewrite this, as always, just like we did with derivatives. I want to rewrite it so it's an exponent. So we're taking the derivative of x to the negative second power. So just like before, we're going to add 1. So negative 2 plus 1 is negative 1, divided by negative 1, which plus c, which is just negative 1 over x plus c. So that's another power rule. Going down, so again, we are going to rewrite this so it's an exponent. So this is t to the 1/2 dt. So we add 1 to our exponent. So 1/2 plus 1 is 3/2, and then we divide by 3/2 plus c. Now we're dividing by a fraction, which is the same thing as multiplying by the reciprocal of that fraction. So this is 2/3 t to the 3/2 power plus c. Now this one over here, this has 2 terms, but that doesn't really change too much. We're just going to do one at a time. So the first one is y to the first power. So we add 1 to the exponent. So it's y squared divided by that new exponent. So y squared over 2. And then plus 2y. That's one of those rules from above, plus c. So this leaves us with 1/2 y squared plus 2y plus c. Moving down. So this is theta. That's just the variable we're using in this one. So we've got 3 terms. Just take the antiderivative of each term. So the first one is 2 theta, add 1 to the exponent, divide by the new exponent, and then minus 3 theta, add 1 to the exponent, divide by the new exponent, plus 1 theta plus c. So then that just leaves us with 2/3 theta cubed minus 3/2 theta squared plus theta plus c. And again, I'm going to say this for probably the 4th time. You can check that you're right by thinking about what the derivative of this would be. If you end up with what you get in your integral up here, then you are correct. So number 6. Now we haven't talked about any kind of quotient rule, and that's because there actually is not one for antiderivatives. But in this particular case, we can rewrite this so it's no longer a quotient. So this is the same thing as x over the square root of x plus 1 over the square root of x dx, which is the same thing as just subtracting exponents here. So this would be x to the first over x to the 1/2. And if we subtract those, we're left with x to the 1/2. And then plus x to the negative 1/2 dx. And if we integrate that, add 1 to the exponent, so x to the 3/2 divided by 3/2 plus x, add 1 to the exponent, so negative 1/2 plus 1, it's positive 1/2, and then divide by that new exponent, plus 3. And then just simplifying that a little bit, just because I don't like the fractions in the denominator, we multiply by the reciprocal. So 2/3 x to the 3/2 plus 2x to the 1/2 plus c. And those are our basic antiderivative rules.